Today's speaker, Chris Tully, is no stranger to PPPL. With the help of Charlie Gentile and laboratory technicians, he set up a laboratory in the basement of the TFTR test cell to detect Big Bang neutrinos, whose discovery, he says, could potentially transform our understanding of the early history and evolution of our universe. Chris is also no stranger to big discoveries. He was a member of the team at CERN whose work helped lead to the discovery of the Higgs boson, which brought the Nobel Prize to the original Higgs theorist last week. Chris earned his bachelor's in science degree from Caltech and his doctorate from Princeton, and he's been a professor at Princeton for the past 13 years. He was a CERN fellow from 1998 to 2000. He was a recipient of a Sloan Fellowship in 2003 and the IBM Einstein Fellowship at the Institute for Advanced Study in 2010. His publications include the textbook Elementary Particle Physics in a Nutshell, which Princeton University published in 2010. So without any further ado, please welcome Chris Tully.
Oh, thank you very much. It's an honor for me to be here today to talk about this experiment. I've really enjoyed working this last year with many of you, and this gives me a chance to sort of give back and talk a little bit more about the science we're doing. So before I talk about the Big Bang, I thought I'd like to start out by just talking about time. And a person once mentioned to me, I was always fascinated looking up at the sky at night, because he realized that what he sees doesn't really exist in the sense that it's all there in one place at the same time. Some of the objects in the sky are a few hundred light years away, but others, like this one here, the Andromeda Galaxy, is 2.5 million light years away. So we see it as it was back then. And I like this one in particular because in the month that I was born, which was in February 1970, there was a survey of the solar systems that were orbiting the galactic center of the Andromeda. And from that data, they showed a very clear picture that despite what we see optically, there seems to be a huge diffuse cloud of matter that we can't see that is filling up the space around the galaxy, so that when you compute the orbital velocity of the solar systems about the galactic center, you have to account for the mass in this spherical volume for which you can't see what's giving the mass, but it just seems to have to be there in order to get all the velocities to work out. And so that was sort of, one of the seminal works of observation of the need to have dark matter in the universe. But what I was thinking is that, when I went to learn physics, let's say 15, 16 years later, no one mentioned dark matter to me. In fact, I don't think I heard of dark matter until I was a graduate student. And I'm thinking they didn't want to scare us away, by saying that, despite our knowledge of Newton's laws and Kepler's laws or even Einstein's law, there's just some big mysterious element of the universe that we can't explain, but we have to put it into our theories. So another question you might ask is, we see this thing 2.5 million light years away. How far back in time can you look? Can you look at the beginning of time? I'd love to see that. And the answer comes from a modeling of the Big Bang theory of the universe, and is that we can see back to about 300,000 years after the Big Bang, and that's the point in which the universe became optically transparent. And so this is sort of an image of the timeline. Let's say we're here, and if you were able to, you grab light, which you can. Light emitted 13.7 billion years ago from some other point in space is just arriving, at the Earth now. And if nothing got in its way all that time, you could construct the map of the temperature, using the photon as a measure of the temperature of that time, of what's called the cosmic microwave background radiation. And some of you might know, Princeton was very central to sending up a satellite at one of the Lagrange points And they found all of these spots where photons hadn't been absorbed yet, and they measured above the galactic background the cosmic microwave background radiation. So that's supposed to be 300,000 years, or the surface of last scattering. Then there's a period which actually they're called the dark ages, where it's and the stars haven't formed yet, and then you have all of this structure formation of solar systems and galaxies. And with that data, an incredible amount of things have been learned about the universe we live in. And so models are applied to the data to try to explain what it's made up of. And those models not only have to account for the gravitational wells and the distances between matter, but also the fact that the universe is expanding. So if you look at the length scale studies of the microwave background radiation, also the large scale structure of the universe, one discovers that we're in this little piece here, 0.03%, the heavy elements of the universe that came from exploding stars. Then there's a piece which is the visible mass from the stars that we see from surveys, and also the free hydrogen and helium content. And then there's these other pieces, which we're not able to measure directly, but we infer them to exist based on dynamical models for how the universe evolved at that time. So there's one piece, the neutrinos, which I'll talk more about, which is an order of magnitude more content than the heavy elements. And then there's this piece called the dark matter, which is not the same baryonic matter as makes up the nuclei of elements, but it has a different set of interactions, but it has a sort of what's believed to be a particle nature and finite mass. And then there's this big piece called the dark energy, and in some sense this is the negative pressure that drives the expansion of the universe. And no one knows what that is, but it seems to have to be there in order to explain the universe that we live in. So as a Princeton graduate student, every student that arrives at Princeton in the physics department learns right away that in 1965, these four Princeton fellows, Bob Dickey, Jim Peebles, Roll, and Dave Wilkinson, had a model for the thermal history of the universe, where on this scale they start back here, I guess, at the 10th of a millisecond up to 10 to the 16 second, to the present day. And they tried to figure out when the universe was optically transparent and other transitions that occur. And they put this paper together in 1965, and they were all geared up to measure the cosmic microwave background radiation, which is predicted when the universe becomes optically transparent at 300,000 years. And unfortunately, Bell Labs, Penzias, and Wilson also had microwave horns looking at the deep space, and they saw it first. They didn't know what it was, but they saw it. So they missed the Nobel Prize for this discovery, but it was right at the tip of the fingers, and they knew what it was. And so when you look at this plot, there are some important features of it. One is this optical transparency, because we can still measure those photons today. The other is this transition point here, which I'll come back to. And that's at the point where if you look at where the energy resides in the universe, there's a transition between having a radiation-dominated universe, where most of the energy is in photons and light elements, to one in which it resides in the baryons and the more massive particles. And this is called the matter radiation transition point. And then there's this point way back here, where you can see a pull away. And at that point, at 1 second, that's when the universe became transparent to neutrinos. So before that time, the density of the universe was such that the neutrinos would continuously scatter on the matter and stay in thermal equilibrium. And my first thought is that's almost impossible, because one way we often say we like to scare young children is to say that if you release a neutrino, let's say in an MeV scale, you need 3 light years of solid iron before it'll interact. And so you think, well, how can the universe supersede the density of iron by such a large amount? And it's because of the atomic spacing. So the atomic spacing you know, if you take the difference between sort of 10 Fermis of a nuclei size and, let's say, an angstrom for atomic size, you have a good 4 orders of magnitude, which then in volume cubed, you have 12 orders of magnitude, and you can quickly take down several light years down to something that's on order fraction of a millimeter. So it describes a period of the universe in which the nuclei, although they're not cool enough to have bound into neutral atoms, but they're close enough that the neutrinos couldn't get out. And there's been a lot of great confirmations of the Big Bang theory. So the relative abundance of deuterium to helium to lithium, they all come out of this period between sort of 1 to 15 minutes after the Big Bang, which is called the nucleosynthesis period. And there's some tensions in that theory, but it generally describes, here this was the point at which helium could be formed. And so I got interested in this problem of whether the neutrinos could be detected. And so in the prediction of the standard Big Bang theory, the neutrinos, when they're released, there's actually not believed to be, you know, a matter-antimatter asymmetry in the neutrinos like we have in the baryons or in the fact that we have electrons everywhere, not positrons. They're believed to be, because at the high temperature at which they decoupled, an equal number of neutrinos and antineutrinos. And there's predicted to be, with a pretty rigid prediction, something like 330 neutrinos per cubic centimeter everywhere in space. And it's sort of an unavoidable prediction of Big Bang theory. If you ask how many electron neutrinos there are about 56 per cubic centimeter. And so, you know, how much energy do they have? Well, it turns out that because they decoupled at such an early point, they actually decoupled before all of the electrons and positrons annihilated with each other. So they end up being a little bit colder, the cosmic microwave background radiation. They're about 1.9 Kelvin. But in energy, they're about 1.7 times 10 to the minus 4 electron volts. So they're, you know, sort of 5 orders of magnitude less energetic than a single photon of light. So they have very little kinetic energy. And as I'll describe, we've learned a lot about neutrinos since 1965. And so there's a lot more things that may be possible today. But I'd like to discuss a little bit about this matter radiation transition of the early universe. So we have a couple of forms of inputs. One form of input is this image of the temperature fluctuations of the photons that came when the universe became optically transparent. This is actually Planck data. And if you can imagine, what they do is they look at length scales across which you see sort of hot spots. And they can look and see how much, if you think about all the modes that are in this fluctuations there, how much power is in given different length scales versus other length scales. And then they can look at the current universe. This is just a near-field view of the galaxies that are around us. This foreground here is just the Milky Way. I think Andromeda is maybe in this M31. And they can look and they can do the same sort of analysis where they imagine after gravitational models you still have some length scales that relate the mass distributions in the universe. And they can try to figure out when exactly the matter radiation transition occurred. And it turns out it's supposed to have occurred about 70,000 years after the Big Bang. So it's before the radiation was emitted. So the photon data sort of cover a set of length scales that cover the period of time during which the transition occurred between matter and radiation dominance. And then out here, this is the Sloan Digital Sky Survey of 205,000 galaxies. This is data by looking at where the galaxies are today. And what they try to do is by figuring out where this peak occurs, and the peak occurs, what it means is that if there's more matter dominance, then the matter takes over the energy earlier, and so this curve shifts this way. And if there's more radiation dominance, the radiation continues to keep power for a longer period of time. And so what cosmologists try to do is they now go and ask the question using as much particle physics information as they can. They say, well, what are the mass of the neutrinos? There sure are a lot of them in the universe. And they know that if they made them, for instance, 10 electron volt large, it would actually saturate all of the mass that they were trying to put into dark matter. So they can't play with the number too much. And they can kind of fit for it. They can't figure out how much mass each individual type of neutrino has, but they can fit for the sum of the masses. And you can see these curves here. This is a green curve. And this is if the sum of the masses of the neutrinos was 2 electron volts. And then here you can see for the white curve 0. And the data, seem to favor the sum of these masses being very small, let's say within the region of 0.2 electron volt. But there are some caveats to this. So this really assumes that there's nothing new in the early universe. So if there were other forms of light neutrinos, which I'll talk about, which are sometimes referred to in general as dark radiation, that would push the curve in the other way. It also depends on the amount of dark energy you put into the fit, so it depends on other parameters. So what particle physicists did is, instead of relying on trying to sort of infer everything that happened, they tried to go in and measure property by property so that we could have more constraints on the stuff that we don't know about. So one of the things that was done, and in fact I worked on this in the late 80s when I first went out to CERN, it's the first measurement I was involved in, we counted the number of neutrinos. So we were able to produce one of the neutral vector boson called the Z boson, the heavier version of the photon. And we produced it in E plus E minus collisions with a center of mass energy of 91 GeV. And then we just watched in what it would decay to. And since it is a particle that lives for a finite amount of time, it turns out that it has a finite width and energy. So it's like any kind of large, a low Q resonance where you can ring it for several different frequencies and still get it to run. And by fitting, using standard model, our now very powerful standard model, we could fit for how many neutrinos were coming from the decay, and we got something that was in pretty good agreement with 3. This actually is still the most precise data on this measurement. It's maybe 2 sigma low. So we measured the number of neutrinos. Now, with that said, these are the neutrinos that interact with the weak boson. So that's how they're defined. The other thing that has been done over the last decade is they've been able to make larger and larger mass experiments in which they can actually get a reasonable number of neutrinos interacting in the experiment. So they have very, very powerful sources. And an amazing thing has happened. So of the now, 50 years of measurements, first starting with the solar neutrino flux coming from the sun, and then sort of more focused in the early 90s on atmospheric neutrinos that are produced in association with cosmic showers, most of which come from pion decay. They're muon neutrinos. There's been a lot of dedicated measurements with reactors, most recently the Diabei reactor in China, and also through accelerators. So these so-called long baseline accelerators like the Minos experiment or Opera. And they've been able to sort of figure out the picture of the neutrinos. And it's very much different than we thought it was. So we thought there was an electron neutrino, a muon neutrino, a tau neutrino. We thought there'd be 3 families, the way there's 3 families, distinct flavor families of other types of particles, for which we found them all. But it turned out that they don't really distinguish themselves by family. They're mixed up. So there are 3 states. They have different masses, but each one has a little bit of electron, a little bit of muon, a little bit of tau. And we've learned what the splittings of the masses are based on seeing them, because if you produce them in a state for which all possible masses could be produced by quantum mechanical uncertainty, then until you measure it, all the possibilities will oscillate in time. And when you make the measurement, depending on how far away you were from where it was produced, you'll get a different probability to get one of the different mass eigenstates. That's how it works. And so they know that there's at least a mass splitting of 0.05 electron volt that's in the neutrino family. And then they know another mass splitting, which is about 2 orders of magnitude, or it's about an order of magnitude smaller. But they don't know whether these guys are heavier than this one or vice versa. They do know this order. And so this is known as the normal and inverted hierarchy. And so we don't know, and there's a lot of experiments that are trying to figure this out. The other thing we don't know is we don't know what the absolute mass of the neutrino is. So the lowest one could be 0, but it also could be 0.05. So there's a big uncertainty on these masses, but the key number I want you to pull out here is this 0.05 electron volt. So, and even in the particle experiments, it's not 100% sure that that's all there is. So if they look at the data, the data do sort of favor the idea that maybe there's yet another type of neutrino, which actually comes out of the notion of the right-handed neutrino. Right-handed neutrino in the standard model has no couplings. It has no couplings to the standard model. It only can be seen through the Higgs mechanism. And so the idea that is maybe some of the dark matter in the universe is made up of stuff that just doesn't have the interactions that we have. And it's just weakly related. And so there's this idea that maybe we can figure out what the dark matter is, or forms of dark radiation, by its small mixture with the neutrinos that we do know. So what is the experiment? Let me tell you about the experiment. Relic neutrino detection. This actually, and if you look at the date, it's quite amazing. So this was actually worked out in 1962 by Steven Weinberg, who has the Nobel Prize for the construction of the standard model. And he had a different model for what the universe might look like. It was kind of a cyclic model. But he realized that if there was lots of neutrinos everywhere in space, that maybe the best way to detect them is by capturing them. So if you have a lot of neutrinos in space and you have a nuclei sitting there, there's a process in which the neutrino can be captured in the initial state, and then you just, instead of having beta decay, where you have the final state nucleus, an electron, and neutrino, you just have the nucleus and the electron, and therefore, in that case, you don't have a beta decay spectrum like you would with tritium, but you would just have a monochromatic peak of electrons coming out from tritium, and in fact, that peak would be a little bit more energetic than all the other electrons coming out from tritium. Because in this case, you actually gave it the mass in the neutrino, and it doesn't have to pay the price of producing a neutrino in the final state. So you would get a peak that's 2 times the mass of the neutrino above the endpoint. And we know from cosmology and from these particle physics measurements that it looks like we should be looking in the range between 0.1 electron volt to 0.6 electron volt, because there's enough data now to say that there should be something there. Now, we don't know how much electron flavor is there, but there's a good indication that that's where some of the neutrinos are. And so why tritium? So I'll talk about that in a moment, but it turns out tritium is uniquely special for its ability to capture neutrinos with a high cross-section. It's in a multiplet that allows super loud transitions, and it has a reasonably long lifetime, over 12 years half-life. That those two properties in themselves make it the most promising material to detect the relic neutrinos. And in fact, these 3 people, Alfredo Coco, Gaetano Mangano, and Marcello Messina, they're all part of this Ptolemy experiment as well, because they also determined from their studies back in 2007 that tritium would be the ideal material to try to detect the relic neutrinos. So let me talk a little bit about, tritium experiments that have been done in the past. Almost all of them have been done with diatomic tritium. And they did this mainly because the calculation for the diatomic tritium binding energy had low uncertainties on it. But at the same time, the bond strength is something like 4.6 electron volt, about 4 electron volt. And what happens, you have two atoms of tritium in a molecule, and one of the tritium decays to helium-3 and emits an electron neutrino. The helium-3 stays bound in a molecule. So it stays bound in a tritium helium-3 molecule. And it turns out that causes all sorts of complications because the molecule is not symmetric. It can vibrate. It can rotate. And so there's all these potential quantum mechanical states that the molecule can fall into. And when you want to measure the energy of the electron coming out and make sure it's precisely above the endpoint, you suffer from all of the smearing of the endpoint because of all the possible final states of the bound state that this falls into. And so sort of the quest for improving upon the ability to look at the endpoint of tritium has been to try to find something with a bit lower binding strength so that there isn't as much uncertainty in the final state. And this is an example of the level diagram, and I don't expect you to read it, but it just shows that if you have molecular diatomic tritium or two atoms of tritium, that the available energy that goes to the electron is affected by that bond strength. And if you looked at the energy spectrum of the electrons coming out, depending on how strong the strength was, you would get a shift in the spectrum. So it turns out that this issue of having a lower bond strength of hydrogen isotopes is actually very closely related to hydrogen fuel cell research, where instead of storing hydrogen either cryogenically, which would be very expensive, or under high pressure in a gas, which requires quite a thickness of steel, the idea is to store it in a solid form in the sense that it would bind on the surface of some material at room temperature, but if you heated it up to like 600 Kelvin or something like that, it would come off. And so one of the one of the materials that's heavily researched for this use is graphene. Graphene had been theoretically predicted for many years, and I guess the Nobel Prize for it was given maybe 6 years ago. But effectively, you have a carbon. It's only carbon, and it's in this case, it's wrapped in a tube, but you can see it has this sort of planar configuration, and it's just carbon-carbon bonds everywhere. Now, it's very conductive. So there's a free electron in each carbon, and in fact, for its thickness, compared to gold, it's a much better conductor than gold, even though it's just a carbon structure because of this regular geometry. And one of the favorable things about it being a hydrogen fuel cell candidate is that in this picture, where each hydrogen binds on each carbon, you can see it sort of alternates on the inner and the outer case, you would get sort of 6% by weight storage of hydrogen, which is sort of what the spec they're looking for the hydrogen fuel cells. And the hope is that this binding energy is less than 3 electron volt, and it's not clear exactly how low it is, and that's something that one has to determine. Now I see that Bruce is here, and I've tried to learn as much as I can from the chemists, and I realized that to figure out the binding energy, unless you have a good method of determining it directly, can be quite complicated, because you have to know there's a cracking energy, which is the splitting of the diatomic molecule to atomic model. But not only does it absorb onto the surface, but depending on how many absorbed and what the geometry is, the binding energy can be different. And in many measurements, what they do is they heat up the substance, and they look at how much gas comes off for a given amount of heat putting in. It's called the deabsorption measurement. And they try to infer from modeling what's going on what the binding energy is. Now, unfortunately, in our experiment, we need to know the binding energy pretty well and the range of binding energies. So one of the proposals for the project is to develop, for instance, different geometries of graphene, such as this nanotube or different planar structures, and to try to measure it. So when in doubt, measure. And one way to measure it is to actually just to put this tritium on instead of hydrogen, and then just look at the differences in the endpoint spectrum relative to diatomic tritium where it's well calculated. So that's one of the new things we're looking at, and it could be that this might be a fruitful tool for even the hydrogen fuel cell research. And I was also thinking, well, if there's all of these side impact of hydrogen fuel cell research, could such an effort actually help fusion research at all? And there's a possibility for that. In fact, I worked a good 3 or 4 years back. Charlie and I and Adam worked on projects involving the neutral beams. And the development of those beam systems hasn't been that active. And if you look at the possibility of, instead of sort of cracking the diatomic deuterium, let's say, to produce an ion source for those beams, you could potentially save on that energy by having already, let's say, deuterium held into a fuel cell-like geometry. And as I'll show, like the Ptolemy geometry where it has a magnetic flux going through it, you could actually extract the deuterium into the injector without paying the inefficiency of the sort of ionizing that plasma before doing that. So as I'll show with the structure of the cell, how that might be possible. So, but what is the challenge? If this problem has been around for 50 years, why haven't people measured relic neutrinos before? And the problem is, even if you take tritium, which is the most attractive isotope for which you could capture neutrinos on, what you find is that you need 100 grams of it in order to get enough of a rate per year. And the more difficult thing about it is when the neutrino captures on the tritium, the electron that comes out from that capture, it can't scatter through much material. So you have to bring it out and make a measurement of it without having it go through, a lot of, let's say, layers of other hydrogen or going through other materials. And if you ask how much surface area you need to hold 100 grams of weakly bound tritium, it's about 200 football fields. So it's just some enormous, outrageous thing. And in fact, Frank Calaprice at the department, he said Steven Weinberg had called him back in the 60s to ask about doing this experiment. And Frank came up with the same answer right away, saying the surface area is way too large, and it's sort of an unavoidable impasse to do such an experiment. But, things have changed over the years. And the nanotechnology opportunities that we have for developing these cells make it look feasible to develop such a system. And in fact, with Bob Woody, we had looked into lots of different ways to try to stack planes of graphene, either planes of graphene or, if you can imagine, growing nanotubes periodically with a certain spacing. If you have the magnetic field running through the planes, then when the electrons come off, they go through a cyclotron motion. And the idea is to deflect them away from that, their guidelines away from the magnetic field line with a transverse electric field. And so the idea is that you would drift them with E cross B field so that they get out of the way of the subsequent layer of graphene. And if you can space these tight enough, let's say even 10 micron apart, where these wires are in order between 5, or if they're multi-wall, say 100 nanometers, and you were able to put electric fields in between them, you could imagine building up a structure where you have many, many layers, nanoscale layers of graphene, all of which would be able to absorb tritium on their surface. And when tritium decays, the electrons would be guided out of these ducts because they would be deflected up by the electric field, and they would follow the field lines along that direction. And in fact, we've built up a model for this, and we're hoping to use our new 3D printer to take a look at what the structure would look like to identify. Because you actually would make kind of a fractal system, because the scale here is so small that you would build up a package of these, which again would be the next source. Then you would have a larger electrode outside of that. So eventually you would get up to something, individual elements that were on order size of centimeters. And the actual target would actually be about a meter across. So how do you use such a hydrogen fuel cell? Well, you charge it up. It has a charging time. And again, we would have to measure it for this geometry. But in some geometries, it takes maybe 4 hours for the hydrogen to saturate onto the surface. And one thing that we're trying to do in our experiment is that when the hydrogen absorbs onto the surface, it transitions from being a conductor to an insulator. So if you instrument these nanowires and look at the change in their conductivity, you can actually watch them charge up with hydrogen and sort of get measurement. And you can also even imagine when the tritium decays to see the helium-3 coming out the backside of the cell. So the graphene and the hydrogenation of the graphene is particularly attractive here at PPPL because there is a nanotechnology lab, and I've been working with Evgeny on ideas for how to develop different structures. And so this is a slide that he's made on his method for using cold magnetized plasmas to build up both graphene and also the ideas for hydrogenation of them. And we've begun some initial work on that. So back to the experiment. So 100 grams. So you need 100 grams. That's something that's sort of invariant. It just counts the number of nuclei that you have in the system, and you need sort of 10 to the 25. The other thing that you is the capture cross-section, in this case times the velocity. And that's just flat over a big range. So neutrino energies all the way up to 10 keV, they all have about this cross-section. And then it's just a straightforward calculation. There's some uncertainties on this cross-section, but it's just the number of nuclei, the cross-section, the Big Bang prediction for the number of neutrinos, and this is just the speed of light and the number of seconds in a year, and you get a prediction for about 10 events per year. So 10 events per year, from a particle physics point of view, sounds like a lot, for a signal. But if you compare it to all of the tritium beta decays, which are 14 orders of magnitude higher than that rate, you would start to worry that you're looking for a tiny little signature on top of just some massive background. I should also mention that there is some possibility that this rate is larger than we expect, not only from the Big Bang theory being different, but also because we're sitting in a galaxy. And so there is this idea that if the neutrinos were more massive than we expected, then they would clump. And so the local density of neutrinos might be higher. So how does the experiment work? So the experiment starts with one of these tritium cells on one side.
How many of these cells will you have in this experiment?
It's designed, in this case, if the cells are about a meter in size with about a meter squared cross-sectional area, you would need about 10 of them. And as I'll show at the end, the system, the preferred geometry for running enough mass through the system is to break everything up into individual cell containers. And in fact, related to the issue of how much tritium one can store on site, because there are sort of licensing issues with that, one of the goals is to make the container that holds the tritium the DOT spec that allows you to store that mass on site without being in violation of the license. And in fact, I think the UC, I don't know, is it 206 or something, or 602, is a 20-gram storage. So the current storage size that they use, which is about a container of this size, is a 20-gram storage system. So it's sort of compatible with the geometries here. So the idea is that you have the magnetic field lines running through the cell. And what you do is you contain that magnetic flux throughout the experiment. So the electron that's spinning on this field line, it's first accelerated into a higher field magnet, and then it's expanded out to a larger volume. And it turns out that there's a technique called magnetic adiabatic collimation with electrostatic filter that essentially what allows you to do is, if you imagine the electrons produce and it has some magnetic orbital moment, what you want to do with an electrostatic potential to cut off the spectrum is to spin it down. You don't want it to be spinning like this, because if it's only moving slowly and you put an electric field across it, it'll bounce. It'll bounce before it gets there. You want all of its kinetic energy to be moving in a straight line before you put the electrostatic barrier. And so that's exactly what expanding the field lines do. When it's spinning a lot here, when you expand out the field lines, the adiabatic invariant, which is the transverse kinetic energy over the B field, it sort of straightens out the trajectory. And at that point, if you cut at it, you can keep just a small region of betas that are near the endpoint. And that ability to do that is really critical to the experiment, because so instead of having 14 orders of magnitude of extra betas coming your way, you want to get rid of most of them. So it's a filter. It allows you to filter out most of the spectrum. It's actually an advantage of this experiment, as I'll describe later, that we keep some of them. Because by keeping some of them, you can actually monitor the energy scale of the trajectory and the strength of the source and various other properties that you can calibrate all the little microscopic sources against each other. And then after you apply this cutoff, what we've done into the system is what we really want to make sure is that when we measure something, that it's actually an electron that's coming from the tritium. Because if it's a low energy object, it could just come and hit the detector and it came from cosmic rays or it came from background sources. And so a unique feature of electrons, and this was a technique that was really only recently developed, is that when they're relativistic or even just semi-relativistic, a single electron moving in cyclotron motion will put out enough radio frequency waves to be detected with a waveguide. And so in fact, using the same electronics used for the WMAP experiment, it's possible to detect non-destructively the low energy electron as it goes through the waveguide at about 44 gigahertz of cyclotron motion, and to see that it's actually there and it's coming from the source. And it also gives you a time marker, so you know where it's going. And so you can, eventually then you expand it down to its low energy again, and you detect it with a calorimeter, a very precise calorimeter. So this is also, I would say, the main reason this experiment is now possible and was never possible before, which is that in the push to measure the cosmic microwave background radiation, a new technology was developed for measuring energies precisely, and it's called transition edge sensors. So these are sensors that are held at the boundary of a superconducting to normal transition, and what happens is if you heat them just a little bit, they become very resistive because they go from superconducting to normal. And if you have current running through them at the time, that change in that current can be picked up with a squid, a very precise magnetometer, and that's used to measure energy. And so this is actually a design of a transition edge sensor, which is actually this little piece here. It's just titanium and aluminum. And they have very clever ways of altering the heat conductivity between this little piece here and the wall. This is actually this is 300 microns, about this far. So this is a very small one, so maybe only 40 microns across. And in this case, it's actually measuring the ohmic dissipation of the radio frequency waves in an antenna. But in our case, as I'll describe, what we want to do is have electrons hit directly a surface that transfers its heat, and then we record it. And so the main purpose of the Mackey filter is to reduce the rate of electrons that impinge upon these sensors. These are actually the two of the people who are on the project are the two world-leading experts in transition-ed sensors. One is Clarence Chang at Argonne, and the other one is Kent Irwin. And together they have designed all of the transition-ed sensors for all of the major projects in CMB. So we're happy to have them as part of the group. So what's the big challenge with using microcalorimeters? Why isn't everyone doing it? Well, a superconductor, if you put it in a magnetic field, a strong magnetic field, it'll go normal. So it doesn't like to reside in a magnetic field. In fact, it has a Higgs-like mechanism which expels magnetic fields through the Meissner effect. But they have a design, and in fact, this design is very similar to something that they have to do for their normal designs anyhow, where they have to keep microwaves away from the electronics. In this case, what they've done is to guide magnetic field lines to regions that are not superconducting, but they're thermally coupled to the transition-ed sensors. And they've modeled what the precision they can achieve with. And this is the most important number, which is that they can believe they can achieve a measurement precision of a 0.15 electron volt for low-energy electrons. And that is, exactly the same energy scale that we need to achieve to look for the Relic neutrinos near the endpoint. There's also a lot of fascinating technology that comes with this. Because all of these detectors are superconducting, and including the SQUID readout, people have long desired to be able to make large arrays of them. And one of the techniques developed to do that, and has been successfully tested in the last couple of years, is to run microwave multiplexing. So it's very effective to run sort of a gigahertz or a few gigahertz transmission line through the superconductor, and then they can multiplex up to 1,000 channels per line. And this is being developed for X-ray astronomy. And why would that be interesting, in general? One of the reasons it's interesting is actually a completely unrelated field, and that's nuclear material evaluation. If you have, let's say, a reactor that's producing spent core, and they want to send it to France, let's say, to have valuable isotopes extracted out of it, one of the things they want to be able to do is to assess how much, say, plutonium it has in it or various other quickly, so that when they ship it over, it can be validated. Nothing, fell off the ship along the way. And if you compare the precision of the microcalorimeter to one of the highest precision devices that's normally used for this type of X-ray detection, the high purity germanium detectors, then the black is the microcalorimeter and the germanium is the open histogram. They're several orders of magnitude more precise. So you can see lines of the plutonium and distinguish them from americium very easily. And not only that, in this multiplex way, you can actually record the data several orders of magnitude faster than you can with these. So with one of these sensors, which is very small, you'd have to sit there for a day evaluating it, while this stuff can literally just move on a little moving tray and be evaluated within a minute. So there's exciting things with the microcalorimeter. The RF tracking is something that I'm developing with the group that worked on the WMAP. And again, these are waveguides that are cooled down. They normally cool them down in their systems to 20 Kelvin and are able to instrument them with these kinds of amplifiers. And it turns out that although the know-how to do this has been around for some time, no one has ever been able to get a system that's sensitive enough to measure the electrons coming from tritium. And there's, in fact, a project that's trying to do neutrino mass and wants to use this technique. And it looks like at Princeton we have all the know-how and set up to actually figure out whether this is possible or not. And it's supposed to be, based on the estimates. And so that's another exciting new thing we can look at. And so that would measure the radio waves from an electron, from a single electron that's traveling through a waveguide, which is something, 10 years ago people thought be almost unheard of. So we've done a lot of simulation work. So these are magnetic field lines. These are the two high field magnets. This is just sort of to set the scope of the next slides. And this is where we expand out the field. We actually expanded out, so it's 2 orders of magnitude lower field at the midplane, and that gives us 1% cutoff accuracy. So these are the 2 magnets in the basement of the test cell. This one actually can go up to 7 Tesla, and this one 2. But we operating them at fields so that we get about 300 Gauss at the midplane, which we had measured back when we had them both energized. This was a larger central chamber that we had built somewhere in southern New Jersey. And Bill Blanchard and many of us, we had to work quite hard, and Lloyd and Jim, to figure out the bellows system and how to sort of be able to insert and roll out this chamber without moving the magnets. And this is what the system looked like when it's all assembled. So in this case, we have a source that's placed in the bore of this magnet. We expand it out, and we bring it back into a detector on this side. And we have electrodes that set up the electric field cutoff. And this piece was critical because without cutting down on the rate, we could never test whether the technologies for this project would actually be feasible. And so we've taken some data, both with a tritium source, using just a standard, not the microcalorimeter, but a standard room temperature windowless APD. We've also been investigating the use of TFTR cells. We've also taken samples to look to see whether, in fact, tritium on graphene already exists on these cells. And this is a Raman scattering analysis from the PRISM showing that there are different types of graphene in the samples. We're hoping to get future sources from Savannah River National Lab, which is very part of the Ptolemy project and very interested in contributing samples. So one of the main backgrounds, so one of the limitations of the experiment is how much background you have. And since you're going to make all of the support structure out of carbon, one of the backgrounds is carbon-14. And in fact, that could have been a real showstopper. You know, how much radiation does carbon-14 put out? So let me remind you how carbon-14 dating works. So you take some biological sample from a couple decades ago, and let's say that sample of, let's say, 100 grams or so had 100 hertz of beta decays. The biological systems have about 1 part per trillion of carbon-14 in them. And it turns out that carbon-14 is cosmogenically generated. So it's generated, by the cosmic rays in the atmosphere, and that carbon dioxide or the methane and other things, they exchange with our body. And so once we take that out of a biological system, over the period of 20 years, we would see this rate decrease by a fraction of a hertz or something like that. The lifetime is very long. It's 5,700 years. And so if you compute what that carbon background would be to our experiment, it turns out it would be about 1 million times more radiation than the experiment could handle. Even though we're just looking in a tiny little window of 0.05 electron volt near the endpoint, the carbon-14 it was 5 orders of magnitude too large. And so fortunately, other people in low background experiments also experience this problem. They use liquid scintillators, which are hydrocarbons, and they needed to achieve very low levels of background. And if you take carbon, like methane, from out of the ground, it actually is per 10 to the 18 of carbon-14. So those levels have been achieved, in particular the Borexino experiment. And so that background, we believe, can be under control. But with that said, we're actually measuring the carbon-14 transport in the system. This is a spectrum of carbon-14. In fact, we're taking data now where we have carbon-14 in the magnet with an APD, and this is just the high-energy part of the spectrum, so near the endpoint. The challenge in this experiment is not only to meet the precision to measure the endpoint, but also to control the backgrounds. Now, this is in some sense, the competing experiment. It's called Catrin. In fact, I picked the name Ptolemy because I was thinking Ptolemy and Catrin, it's sort of like brother and sister. And now Catrin is also at a fusion laboratory. It's at the Karlsruhe laboratory. And the Mackey chamber, instead of that one that I showed you, it's in the basement of the test cell, it's actually more like 5 stories high. And the difference between that experiment and the Ptolemy experiment is in this experiment, they don't try to measure anything. They just want to detect whether the electron made it past the cutoff. And so they make the cutoff very precise, and you can make it very precise by expanding the field lines instead of 1% of their strength to sort of 10 to the minus 4, 10 to the minus 5 of the strength. And so they have very narrow solenoids, and they expand to a very large volume. But the difficulty with that is since all of your signal comes at the midplane, anything that has very low energy that enters at the midplane, which is huge, gets accelerated back in and gets counted. So they've already measured what their background levels are, and it's about 10 millihertz, and that's about 5 orders of magnitude larger than the goal for the Ptolemy project. And through the combination of the RF tracker and the magnetic geometry, we believe that we can bring this level down significantly, but that's one of the things we need to measure. So what about the geometry? So if we did validate the tritium cell geometry, that we can build it with the nanostructure as we want, if we validate the microcalorimeter that reaches the precision we want, and the RF tracker so that we can do the particle ID, would we build the same thing? Would we build exactly the same thing? And the answer is no. In order to actually have enough mass capacity for the system, this idea of having these 2 little bottlenecks ends up to be a limiting factor. So a more favorable geometry is one like a dome, where you have several sources coming in, so you can have multiple cells, and you expand out. This is the field lines being expanded. And we were really only looking on this side, but the side could actually be made more symmetric. And you would have sort of electrostatic filters being concentric shells. So I went as part of an exercise in the neutrino community. We looked at all the future experiments that were proposed for the next 10 years. And this is a list of them. So neutrino energies cover, an enormous gamut of energy, in this case 22 orders of magnitude. There are neutrinos that come from the sun. There are neutrinos that come from the middle of our planet, the Earth. There's reactor neutrinos, neutrinos from supernova, accelerator-based, cosmic rays. And there are special experiments like the instrumented ice of Antarctica that look for extragalactic sources of neutrinos that are even more energetic. And Ptolemy is uniquely the only experiment that is tackling the Big Bang neutrino problem. And there was quite a lot of support shown for the direction that's going. In fact, it uses a lot of technology that are similar to these experiments. So we're very happy with how that came out. So let me just talk about, the impact of such an experiment. And I say this because, believe it or not, for, the 2 decades I worked on the Higgs search, people would often say, why bother? No one will care. You have a model that basically describes what's happening with the elementary laws of physics. And, whether it's there or not, nobody's going to care. Well, it turns out that they did care. And now they're worried about it. Now that they see that there's a real scalar particle in the universe, they want to know where it came from, what influence it had, what makes it, have an energy scale that's stable. And I think if you look at this cosmic neutrino background, even though there's a very definite prediction, 56 neutrinos per cubic centimeter, it has the same list of potential insight. One is that the number could be very different than we expect. And so there are possibilities to get an outcome that is inconsistent with Big Bang cosmology. And that would be, a real turning point for that understanding. There are also possibilities where there's something new in particle physics. You know, non-relativistic neutrinos that have been sitting around for a long time is a very hard source of particles to come by, and it could be that they have a finite lifetime, that they decay into some other form of matter that we don't know about, and that when we go and look and we have the right sensitivity, we don't find them. You know, they were there in the early universe, but they might not be there in the present day. And there are also variations of the interactions between neutrinos that we might not understand, that it would change the amount of neutrinos in that spectrum. Is there a chance for discovering new physics? There's this great uncertainty about sterile neutrinos, whether there are other light relativistic degrees of freedom. In fact, the cosmology data favor a little bit more, maybe something a bit heavier than neutrino, so it's not completely in thermal equilibrium, but there is a possibility that we could discover contribution to dark matter or dark radiation by looking above the endpoint, and in which case that could have an energy that's up to 10 keV above the endpoint. It would be a much clearer signal because it's farther away from the beta decay. But in general, if some physicist comes and tells you you're sitting in a pool of neutrinos and you will live your life that way, you know, it's one of those things where you really have to ask yourself whether it's really true. And so this is one of the ways we can actually use our technology and go after that question and maybe learn something, you know, very deep about why we are here. So there's still a lot of R&D to be done on the tritium, the detector, and the background levels. But the prototyping has been an excellent experience here. We've really been very productive. And we look forward to opportunities where we're collaborating with different parts of the lab, and we hope to some of the things that we're doing will help in other areas. And so finally, this is a list of the many people who are working on. There's Charlie. Adam's not here, but there's Bill and John and a large group of us. These are some of the students who worked with us over the summer. And it's been really a pleasure to discuss this with you today. Thank you. So that was it turns out that was the first thing I computed, because I was worried. In fact, I talked to a fellow, David Spergel, on campus. I was worried that, I don't know if you're familiar, but in dark matter experiments where they're trying to measure dark matter directly, they don't have much room to expand because the solar neutrino flux and the interaction strength is large enough that they'll just start counting solar neutrinos. And so they'll have a background in their spectrum. I computed it for the solar neutrino flux. The solar neutrino flux peaks at around 200 to 300 keV from the PP neutrinos. And in 1 year, with 100 grams of tritium, you expect about 1.5 neutrinos to interact at 300 keV. And but below that, it's just 0. And then if you go and you say in this one little 0.5 electron volt region, it's absolutely 0. The other type of neutrino I was worried about are neutrinos that are emitted from the sun. They're not an electromagnetic transition, but they're actually a weak transition. So you can get these thermalized neutrinos that have a kinetic energy that's the energy of the sun, which is about 1 keV. So I was worried there'd be all these 1 keV neutrinos coming from the sun. And again, it turns out that the flux is just so small that it's not detectable here. There really are, I guess the impression that you should be left with is there really are a huge number of neutrinos. It's an order of magnitude more than the matter we're made out of. Yeah, it's cross-section times velocity up to 10 keV. So what happens is that if you want to measure solar neutrinos, many of which go up to, let's say at 300 keV or even up to like the 15 MeV range, you can actually get much more interaction cross-section because then the cross-section does pick up because the phase space goes up. But it's completely flat below 10. Uh, I was thinking that, and actually I have a proposal I put together. And the experts in the field, they're most worried about the graphene, the uncertainty of the binding energy of the graphene, and they'd also like to see that the microcalorimeters actually deliver on their promise. So I'm proposing something where I would look at tritium on graphene of different structures and directly measure the bond strength by just propagating the betas from a small sample into a microcalorimeter. So the smallest system I need is a dilution refrigerator with the microcalorimeter and just some samples of graphene with the different levels of tritium that goes through the Mackey filters. The Mackey filter handles the rate, and I've worked with a Janus engineer for a non-magnetic dilution refrigerator that will pipe the electrons into it. And I think once one verifies that one can see very clean edges on the spectrum and the shift between, let's say, diatomic tritium and tritium on graphene, I think the uncertainty about whether the project should go on would be gone. In that, I would also like to test the RF detection, but that's just a little thing I would place in between.
Do you have a drawing of how you actually would put this thing on the floor when you've got these big cells with the magnets?
You mean above in the test cell or in the basement of the test cell?
You've got an experiment. You've shown a lot of the concepts, and indeed for colloquium, that's great. But is there a drawing of the experimental apparatus as it would appear on the floor?
Yeah. It's an archive note. It has the full technical drawing of how the Mackey filter fills into the dilution refrigerator.
If you've got 10 of these cells, that means there's 10 magnets? Or
No. Oh, okay. No, for the full-scale system, I have only a complete drawing of the prototype. Yeah, for the system where you have a dome, you actually decouple the geometries of the source and the calorimeter and the RF tracker by using, in fact, Bob Woolley came up with this idea of magnetic ducts. So as long as you can keep the magnetic flux line closed, so if you imagine that I had a solenoid or a torus that went up here and continued all the way around here, all the flux lines would be closed. So in this experiment, you essentially open up the gap to expand the magnetic field lines in an open volume. That's where the Mackey filter is done. And then you open up the torus again in the region of the source, and that's where you drift the electrons out. So it's really just a magnetic closed-loop flux torus with gaps in it, where you have one gap, which is the source, one gap, which is the Mackey, and one gap, which is the microcalorimeter.
I sort of understand in general, but I'm an old fart, and to picture all this, it would sure help to have a drawing.
Sure. You know, that's actually how it was advertised in the report, which is that people are really looking at this as a way to push beyond the Katrine-like neutrino mass measurement. So even if you don't have enough mass in the system, you can still make a very critical measurement in particle physics by looking at the shape of the endpoint spectrum and to infer that what the mass of the neutrino is from that.
So then, you better look at actually, you treat the source nearby, and you actually measuring this mass from close to the.
Yeah, I'd love to do that. Like any. See, I think the thing is, I come from community in particle physics where we don't trust anything. We calibrate everything, we check everything, and one of the things we would love to do is, of course, just put a flux of neutrinos on the thing, and to see whether the capture cross sections are correct. And even if it has a finite kinetic energy, which almost all neutrino sources will, you can just measure what the spectrum of kinetic energy of the neutrinos are. And I have been in discussion with the spallation. It turns out the spallation neutron sources have a large flux of neutrinos. Their spectrum sort of peaks around an MeV. But I think the system could be adjusted to meet the dynamic range of MeV energies above the endpoint. And it's a real possibility. But you have to go to something like a spallation source. reactors produce anti-neutrinos, unfortunately. Well, so that's what can't happen. So the limitations of the current limit on the neutrino mass measurement actually came from the fact that they stacked condensed diatomic tritium on a surface, and they had about 100 layers. And in fact, I think they were gettering, some hydrogen in the system from the vacuum, a UHV vacuum, onto the surface too. So they didn't really understand how much material they were going through, and that was the main systematic. In our system, you can. So in the Katrine system, they have a gas column. They actually inject 20 Kelvin diatomic tritium into a magnetic field, and they suck it back up again. And they hope that nothing makes it into the chamber, because that would mess everything up. But the problem is the length of the column. So no matter what you do, the electron's always faster than the gas. So the length of the column tells you how much scattering there is. So what we've tried to do here in the solid geometry is to make it so there might be some scattering of the electron near the carbon, but maybe only about 1 or 2 interactions. And 1 or 2 layers of carbon is okay, even though it goes like z squared. But then after that, if it's a high purity vacuum, then we really are trying to eliminate all possibility for scattering. So the length, we really want the length scale for the scattering to be on order 10 meters, which has been achieved with Katrine.
So there's no scattering when these things come off the carbon and you cross the field, there's no danger of them sort of grazing the next plate. It's only 10 microns away, that kind of stuff.
Yeah, that's right. So the E cross B will be set so that there be no probability for excursions into the surface. Now, what can happen in these systems is you can have a background, that comes and it showers, high energy particles through the system. But it turns out that those particles really will have very little aperture for the experiment, because in order to make it out, and in order sort of through the waveguide and all this, it really has to be low energy and has to be created in the magnetic field. So even if you have electrons that are produced near the surface of the cryostat, it just won't be the right energy and it won't be on the right trajectory for the source. We actually have a Geant-4 simulation of the detector, and so far it looks pretty impressive, but with these simulations you always have to be a little difficult. So that's why we're trying to measure some of the backgrounds, and we're hoping to see, for instance, a very clean carbon-14. If we can measure our background, which is the carbon-14 from a standard piece of graphite, and then we'll go down to sort of a low carbon-14. If we can measure that cleanly, I think we have proof that we can achieve the background levels we need, even in this very small system. And it's just because the particle ID.
That plus the seeing how the sort of getting out of the material screws up your peak are the two main things.
Yeah, that's right. Yeah, the main issue is that if the graphene has many structures and we can't control it somehow, then even though it might all be very static, this one might have 0.8 electron volt binding, that one has 0.9, and it has 1.2, and so you still have to average over the system. Now, admittedly, it's all of these cells, all the columns are all run individually. So it's a pixelated calorimeter, it's cell-by-cell RF tracker, and all of the target is separate. But still, if you have smearing within each cell, you can't correct for it, so you have to eliminate it at the source. And it could be that the graphene won't work out. I mean, that's part of the idea of innovative research, so you get a wrong answer.
Is there any issue getting the 100 grams of tritium?
Well, that's one of this. I think that's sort of uniquely the main contribution of our project, which is that we've figured out that there are ways to get the 100 grams of tritium, and if you ask Savannah River, they're more than happy to try to make that possible. But the sort of this concept that was initiated with the TFTR, where the tritium sort of plated onto the tiles, they didn't count that into the inventory, and the same also exception of storage chambers. And so those are the two directions where we don't have gaseous tritium that's going to.
What's the scale of the data processing going to have to do with the size of your experiment?
Yeah, I mean, that actually is quite extensive. Because there's microwave multiplexing, there's on order 10 to the 5 microcalorimeter channels on sort of a 10 gigahertz transmission line, 1 megahertz bandwidth each. And then the RF waveguide all are individually instrumented. We can group those. It turns out you can use this E cross B to sort of collimate things as needed, depending on how much rate you want the occupancy to be 1 electron per transition time, so that's what you have to adjust to. Similarly, I have to say the hope in this project is that we could instrument the target, the cell, so that we can see the helium-3 coming off. We can see the conductivity changes in the wire. In fact, the people who originally did the hydrogenation of graphene, they could actually see individual atoms coming off. They could see steps as the conductivity changed. And that kind of capability would be enormous, because then we would have the time of flight measurement from the source to the detector. So we're still open to the idea of actually instrumenting the cells. Yeah, the bandwidth calculation, it looks very much like an LHC. It's sort of 10 gigabits of data coming off the system. So whether you would record it all or whether you would look at a window around the calorimeter and toss most of it is more likely. So it does require the sort of kind of trigger system where you just don't record everything. You do look at the energy spectrum you're seeing in the calorimeter, and then you window the RF and the instrumentation. Oh, yeah. No, yeah. You certainly have to look at some of everything. That's exactly right. Well, I have to say that the competitor is 11 orders of magnitude less sensitive than the target here. So there's a lot, of ground we can cover between what people can do now. And that experiment hasn't even run yet. People basically have the only constraints they have is from cosmology models. But the goal is to have microhertz or sub-microhertz of noise. So that would only produce on order 1 or 2 background events in 0.5. I mean, the key thing here is it's a very narrow energy window that we're looking at. So you can have flat spectra, but the integrated dose in that window has to be sort of on order 1 or 2 events per year. And so if we find that we get 100 events per year, it would immediately mean that we could, for instance, do maybe precisely the indirect neutrino mass measurement and searches for dark matter, but that experiment in its design wouldn't have the nominal sensitivity to find the relic neutrinos. Because I don't think running it designing an experiment that requires to run more than 5 years to make a discovery, I don't think is very good scientific plan.
Okay, well, thank you very much, Chris, and thanks to everyone for coming.